However, we're going to have one other group of them that is useful, that every single textbook I have looked in joyfully avoids the problem. I hate people who avoid the problem. Once upon a time, about 30 years ago, there was a textbook for this course written by two gentlemen named Morrison and Boyd. Many people referred to it as the Bible of organic chemistry. It was virtually the only textbook that existed for decades, because no one could even write one that anybody would consider. The thing was about that thick. And it was loaded with brutal work. It was a really hostile book. I still refer to it from time to time. It's been out of print since the 90s, so you can tell. I think they were probably dead long before that. At that point, the mentality was that this was a filter course and we don't have to filter what we say because we're going to push you very hard. In the time since then, most people who have written books have tended to take relatively rough topics, things that are a little complicated, and either cut them, like molecular orbital theory is not in most textbooks anymore for cycloadditions, or simplify them to the point that's a bit false. I have issues with that, and I don't do it. I think it's misleading, especially if you see chemistry again one day. I don't want you to be thinking in an oversimplified manner. Here is what your book does. Your book takes this specific amine type thing and ignores entirely how you get here. Leaving you the impression that doing this reaction is the same as the one up above it. It is not. Specifically, this reaction is done in one flask with the base. That's going to cause some problems with that second step of the mechanism where you have to protonate the alcohol, isn't it? This doesn't stick around long in the presence of base. We actually lose it entirely. This is called the Wolff-Kishner reduction. It's typically done in something like ethylene glycol as a solvent. The exact solvent really isn't critical here. There's going to be some water here, but it just has to be a high boiling solvent. Now, for me to have said that, what does that tell you about the conditions? If I have a requirement for a solvent with a high boiling point, what does that tell you? That I have an unfavorable reaction, and I'm going to push it by scorching it. I'm going to push it energetically by raising the temperature, much higher than I would for a normal process. Imine and enamine formation shouldn't require much in the way of heat at all. This does, because you're not acid promoting this reaction. You could, no one does. This is not particularly friendly to acids. If you do it wrong, you end up destroying your reagents. So how does it work? If I don't have an acid, how do I make it work? In fact, I have a base. This is not specific to this ketone. I'm just choosing one that's, different on both sides. It really doesn't have to be. I have this, which is hydrazine. All right. As before, we have direct nucleophilic attack here. That much the other mechanism would have told us. I have an alkoxide, which in water can equilibrate with hydroxide. So as long as I have water present, which I do, I can protonate that. Whether this protonation happens first or deprotonation happens first is a matter of opinion, not a critical one. Well, then what? I'm in a neutral compound now. I have base around. So it's a safe bet that I can neutralize this ammonium ion without too much trouble. And all these steps are reversible as well, just as before. We're not dealing with anything where we have a strong, irreversible step yet. We will. Well, now what? Now I have a neutral compound. I haven't really gotten anywhere though. From there, we're going to have a more serious problem on our hands. Because we're going to have to be dealing with stuff that's not particularly electronically all that friendly. Hence the need for energy, higher temperatures. If you're going to do something that is, by definition, a little bit on the shady side, energetically, you're going to have to pay for it. This is one of those cases. I have a nitrogen attached to a nitrogen. No difference in electronegativity. Let's try that again. No difference in electronegativity, but we have some odd things in reactivity terms. One of them basically looks like this. Is that if I pull that, what's going to happen? Well, that's going to put me here. Now I've got a nitrogen with a negative charge. little awkward. Whether that happens in a separate step or whether it is simultaneous with this is questionable because, as I said, we're under extremely high temperature conditions. So we're doing some things energetically which normally would not happen. This is a hydrazone. The original NH2 was hydrazine. My leaving group, which I warned you about earlier, is a hydroxide. Very, very uncommon. In this case, we're talking about a reaction that takes place probably in the realm of about 200 degrees C. For organic molecules, that's pretty unpleasant. That's pretty uncommon and unpleasant. We don't work that hot most often, so we're putting a lot of extra energy into this reaction. Okay. Now what? This usually is isolatable. You can make this in a separate step with the acid and it would follow the same mechanism as before. Most people do not because you don't care about isolating it. You care about getting rid of the carbonyl group from the original overall mechanism that I drew. So you do it all in one flask and you use the temperature to drive it. What we're going to have is deprotonation of the other nitrogen. Now again, this may be a separate step, it may not be. Generally, this is how it's mechanistically drawn out. By pulling off that hydrogen, I shuffle some electrons down to the carbon. The carbon is very basic. So it's going to go after whatever happens to be lying around that's acidic, like that. Never fails. Now, I have a hydrogen. Attached to where my carbonyl used to be. What's going to happen now? Well, what happens if I break that bond to the N from the carbon? Mm-hmm. Why does that make any difference? Gets us home. Notice that There's something missing here. What is it? The reverse arrow. It's not an accident that it's missing. This is not a reversible reaction. In fact, it's going to drive every other unfavorable step because this is irreversible, which means, essentially, this concentration will always be approximately at zero. So the reaction, even though the equilibria above may be very unfavorable, they're going to gently shift towards this. Once it goes through this, there's no way back. Which means the equilibria will shift and shift and shift, and eventually I'll end up with only this. Why? Why does that make it irreversible? Let me rephrase the question. Why does any solution phase reaction that produces a gas suddenly become, for the most part, irreversible? Because it's a gas. Reactions happen in solution. Gases don't tend to stay in solution. For a reverse reaction to happen, the pieces have to be able to get back together. This has a boiling point of minus 196 degrees C. It is not going to exist in the liquid phase unless you're doing cryogenics. It does not have great solubility in any solvent, nor do most gases for that matter. So you are not going to have much of it around, nor is it particularly good at being a nucleophile anyway, so it wouldn't even, or an electrophile, because the nitrogens both have pairs of electrons. So even a theoretical reversal of this reaction becomes very unlikely. We have a gas which will exit the reaction, have essentially no concentration around to work with, nor is it particularly good as an electrophile. So reversal becomes essentially impossible. Remember, we're talking about very high temperatures to get some of the other stuff to work. So the solubility on this is even worse. Now, there are quite a number of different reactions, some of which you may do in your life, that involve nitrogen as a leaving group. Diazo compounds, azides. Why is that an issue? Experimentally. Mechanistically, you draw it, you go on with your life. Why would you be worried about that experimentally? Why would you be concerned about doing a reaction that produces a gas while at a higher temperature? Why would that be potentially problematic? Pressure buildup. Given that most chemical reactions are done in glass, what happens if pressure builds up in a glass reactor? If you're lucky, it cracks. If you're unlucky, it becomes shrapnel. Any reaction that produces a gas has to have some sort of vent system, otherwise it will create one by blowing the flask apart or blowing the top off, depending on how you've got it set up. But the point is, whenever you see a reaction that you know produces a gas, experimentally that sets off alarm bells. Oh, I got to make sure I have something on here that lets that gas out, otherwise it will find its own way out. Sometimes you will pressurize things intentionally. Most of the time, that's a really bad idea. Most of the time, we deal with reactions that are very slightly above atmospheric pressure, but not high. We generally want a positive pressure of something inert just so that air doesn't seep into our sensitive reactions, that's all. But we do not go up and say, okay, let's put 10 atmospheres into it. This is not your tire on your car. You don't want it pressurized like that because it'll pop. So, this is a long mechanism. It's one that's not in your book, but it's one that illustrates some interesting problems, that you're dealing with a relatively unfavorable leaving group, and the only way you're going to get that to work is pump up the energy. Even at that, it's still reversible until you have a step that, by definition, is essentially irreversible, and that will drive everything else based on Le Chatelier's. So if I had only like 1/100% of this, it's still going to go forward. That's going to drop to 0. Then I get another 1/100% of it from the steps we had already drawn. That's going to go forward. It's going to drop to 0. Then I get another 100%. So even something extremely unfavorable, stepwise, that goes into an irreversible step will eventually be, overall, a useful and reasonable process. But here, you're asking something unfavorable to happen, so why are you pumping up the temperature? Because you have a massive activation energy, probably on the step where the hydroxide gets thrown out, if I had to narrow it down. So, pay up energetically. All right, that is long and painful. We will deal with worse mechanisms than that before the course is over, but this is probably in the top 5 worst ones in the semester. Maybe even the top 3. Definitely not the top 1, trust me. We still have the Robinson to go, so that one is legend. All right, so with that, we're basically done with the nitrogen side of the nucleophiles. We will have some specific uses for imines in making amines. We will have specific uses for enamines in doing alpha substitution, putting something on that alpha carbon where we took the hydrogen off. We will have, of course, a specific use for hydrazones because we can get rid of the carbonyl entirely. So this complements the other 2 methods. If we're next to an aromatic ring, as we talked about yesterday, we can just rip it off. We can do zinc, zinc, mercury, or we can do hydrogen, palladium, whatever. We can basically take that straight off. But that only works next to an aromatic ring. Depending on what else we have in the molecule, we can make a dithioacetal and then remove that with activated nickel. It's called Raney nickel. The process is called desulfurization. It rips the sulfurs out, replaces it with 2 hydrogens. So we have one method, but that one, in a complex molecule, you have to be aware Raney nickel can cause some other problems, so it's not perfect. It's probably a little easier to deal with than the hydrazine method, the Wolff-Kishner, but activated metals that do basically a hydrogen transfer during a reaction tend to cause problems with pi bonds elsewhere. So that one we have to be a little careful with. The above mechanism, the Wolff-Kishner, is thermally very difficult to do energetically. It's much more difficult to draw it out than it is to actually do it. But it doesn't have the potential to really do damage to other pi bonds, and it doesn't require me to be next to an aromatic ring to help activate the carbonyl group. So I get around the limitations of these 2 with that one. So I have complementary methods. Occasionally, more than one of them would work. That's nice. But it's nice to have a backup method in case something fails. Some people don't like handling Raney nickel because as you dispose of it, sometimes it can catch fire. That's not exactly what you want to deal with in life. Some people are very sensitive to smell, so using thiols of any form is really hostile to them. So experimentally, there may be a reason to prefer one versus the other. Logically, there shouldn't be, but there could be.